here. So for today's lecture, my plan was to do some review. The way that I run my review section, so we're actually gonna have two, which is nice. So we'll have some review today and some review on Monday. But the way that I run the review section is basically just to open up the period to questions. So you guys can ask any type of question you want regarding the course material at any point. But to fill the moments of silence between potential questions, I'm going to start off just by summarizing what we've seen in the class, what we've been tested on so far, and what you can expect to be tested on the final. I'll talk a little bit about effectively like what you can expect to see in terms of the types of questions that you'll be asked. And then I'm just going to start working through some practice problems that I have sort of stored away here and there for the class. In this particular case, I'll probably use the practice problems, the first question that I posted in the practice problem set that went up last night. I like that question because it's sort of just a combination of every single unit from the class sort of mixed together randomly. So I think that that's a good way to prep together, because at least then I can kind of help direct you guys towards the type of question that we're supposed to be working on if you need that direction. So yeah, to start off, does anyone have anything in particular they'd like to see or any specific questions that they're curious about? Can you go, yeah, so can you go over forward selection? Yeah, I can go over forward selection. I was just curious if you have any advice on how to decide what method to use for each question, if that makes sense. Yeah, like the easiest way or the most direct way to choose the method to use is to identify the type of data that you're working with. So effectively, everything that we've seen in the class, every test corresponds to a certain type of data structure. And when that isn't true, the only differentiating factor is whether or not the normality assumption is met. Okay, so let's start off. So if it's okay, Bashir, I'll get to your question a little bit later. I'm gonna use my plan, which was to outline the materials to answer the second question. And then once I get the material outline done, I'll go back and talk about the forward selection part, because that sort of fits into the end of it. So if it's okay, I'll come back to that a bit later. But to answer the first question, like we have so we've seen 13 different lecture sets where basically 1, 2, 3, 4, 5, 6, 7, 8, where 8 of the lecture sets have introduced a different data type. And we've effectively looked at 2 possible types of hypothesis testing procedure based off of the data type. Okay, so the very first thing that we covered, just going by lecture set here, was sampling distribution of the sample mean, right? Okay, so then we actually started testing or looking at particular hypothesis tests. So then we did one sample hypothesis test, which I'm just going to call HT/confidence interval. Which was CI. Okay, so then we did 2 sample HT/CI. Okay, so in the first case, right, we always are going to be able to tell if it's a one sample t-test because you only will have one sample of information, right? So if we have one quantitative sample, then these would be the initial choices for conducting inference. Because if you only have one sample of information, you know, those are the only tests that we've seen that handle information from that one sample. Then in the second setting, or in lecture set 3 rather, we talked about two sample HT and confidence intervals. So this particular lecture set actually looked at two different approaches. So we could have two quantitative samples that are paired. Okay, and this is the same thing as being dependent. Or we can have two quantitative samples that are independent. Okay. And again, once we've identified that we have two samples, there's only a select number of tests that we can run on those two samples. The other thing to keep in mind is when we're running two sample hypothesis tests or intervals, we're basically performing inference about mu1 minus mu2. So this is going to be inference for mu1 minus mu2. And those are, again, are the only two tests that would allow us to conduct that type of inference. Whereas here we have inference for mu directly, so the one sample test. Does that make sense so far in terms of how the data structure essentially helps you determine the type of test? Like, and this would be in the simplest case, so it's just starting off. Okay. Okay, so this is basically what we can think of as unit number 1. So this is what the first quiz covered. Right, so here we have quiz 1. Okay, so the second unit is going to be the ANOVA unit. So in the ANOVA unit, we had one-way ANOVA. We had the completely randomized block design. And then we had the two-way ANOVA. Okay, now, admittedly, choosing between the block design and the one-way ANOVA would probably be the trickiest. Well, the block design and the two-way ANOVA is also kind of tricky, but okay, so with one-way ANOVA, we would effectively have, you can look at the data in a number of different ways, but essentially what you would have is 3 or more quantitative samples. Okay. Now, this would be, in that case, or compared to what we discussed in units 2 and 3, this would be the ANOVA that is directly related or a direct extension of those two sample procedures. So we have some quantitative information. We can think of it as like a large collection of data, say like 100 values, but those 100 values have been split into 3 or more groups. Or we can think of it as 3 separate samples, and the samples can be of varying sizes. Now with the completely randomized block design, oh, and sorry, and this would be inference about mu1 versus mu2 versus mu k, right? So when we use the one-way ANOVA, we're effectively trying to determine if there's a difference between a whole combination of means at the same time. Okay, in lecture set number 6, we talked about block designs. Now, what's tricky about this is block designs would also be 3 or more quantitative samples, but they're aligned in effectively a rectangular or square design. Okay, so this would be 3 or more quantitative samples aligned in rectangular or square design. So that effectively means that when we're dealing with a block design, our data is always going to be written out in some sort of square-like or rectangular-like structure. Right? So you might have the treatments across the top. It doesn't really matter in that which way you like write it, but so maybe like this. Why did I do here? Right, so this could be like T1, T2, T3, T4, right? But this can go up to TK. There's no bound on the number of treatments. And then the other issue here is that you have some blocking variable that's also incorporated into in the design. Whatever, something like that. So this is going to be block 1, block 2, block 3, up to block K, right? So with the block design, we have the same goal as with one-way ANOVA. So this is still inference about mu1 to mu k. But the difference is that we're trying to accommodate for the blocking variable. So there are 2 factors that are present in the system, one that we want to talk about and one that is essentially confounding with the treatment that we want to explore and we would like to control for. Now, the last ANOVA type that we talked about was the 2-way ANOVA, and this would actually have a very similar structure to the completely randomized block design. So you can lay the data out in sort of a rectangular or square-like shape, but in that case, you have 2 treatments that are interacting with each other, and you want to explore both of them. So you have an additional level of complexity. Now, just before I talk about that, I will mention that in lecture set number 6, we talked about contrasts / multiple comparisons / residual analysis. Okay. And these 3 units are 3 general units that can be applied in any of the ANOVA situations, right? So these are used for all 3 ANOVAs we studied. Okay. And what we're talking about here is comparing individual treatment means. So looking for where a difference actually exists if our ANOVA said that we should reject the null, and evaluating the normality and constant variance assumptions for each of the different ANOVAs. Okay, so searching for differences among treatments combinations and checking the normality and constant variance assumptions. Okay. So then with the two-way ANOVA, the two-way ANOVA is allowing us to test for differences among the means of two different factors at the same time and consider their interactions. But the two-way ANOVA would actually have a design that's very similar to the block design. So you would have some sort of rectangular or square grid. So I'll just, sketch something out here. So maybe something looks like this. Okay. And then you can divide the grid into units. Maybe like that. And we can go down this way too. Okay, so this would be, we called each of our factors here A and B. So A and B represent particular treatments. So let's say that A runs across the top. So we're going to have A as 6 levels, but it can also have up to little a levels as we defined it before. And then you have B1, B2, B3, B4, all the way up to little b. And this would be B, treatment levels K. I think I just called it little b there. Okay, so up to B, little b. Now, the difference is with two-way ANOVA, you want to explore both of the treatment effects at the same time. So this creates interaction within each of the different blocks where the treatments align with one another, right? So you have basically all of these squares representing an interaction effect for the entire design. The other thing that happens is you get replication. So block designs give only one measurement in each of the different grids of the field. So you only get one response value for each treatment type. With a two-way ANOVA, you get R replications, which is consistent for every single output, which means that you have multiple measurements in each of the different grids or in each of the different units of the grid that I've drawn. So the two-way ANOVA is certainly a more complicated design because you have two treatments that are both of interest to you and you want to study the effect of both. It's also, again, different from the CRBD because you have replication within each of the grid points. So if you were to compare the three of them, the one-way ANOVA is essentially just an extension of a two-sample t-test where you have K independent samples and you want to test if there's a difference among the means across all those samples. The block design is actually the same goal, but you are accounting for a confounding variable. So this takes the data and places it onto like a rectangular grid where each spot in the grid only gives you one value. And then the two-way ANOVA is a situation where you have two different treatments that you want to study. So that two basically places the data into a grid where you can sketch out all of the different interactions that would be possible, but you can have multiple values for each of the different interaction spots. So instead of having only one observation within each of the squares in this illustration that I've drawn, you can have up to R different observations for each of the different interactions. Okay. Now, the other thing to keep in mind is when we study two-way ANOVA, we also introduced interaction diagrams. Okay. And this was something that we utilized to essentially assess the system before we actually went through and conducted the ANOVA. So our interaction diagrams were tools that we utilized to do essentially like a preliminary check about the system to see if we have any reason to believe that there would be an interaction present. Now, with the way that the quizzes broke down, this is all meant to be one unit. Okay, so from here to here, okay, this would have been the second unit of the course. But with the way that the semester broke down, this was where we cut off and had quiz 2. Okay. So the third unit of the course was our non-parametrics unit. So we had the sign test. Okay. Then we had the signed rank test. Then we had the Wilcoxon rank sum test. And then we had the Kruskal Wallace test. Okay, and then that would have been, that's the third unit of the course. And this is where quiz 3 took place. Now, going back to the original question about using, like, how can you identify the type of data? Each of the non-parametric tests would utilize the same type of data as the 1 sample t-test, the 2 sample t-test, and the ANOVA, right? So our sign test and our signed rank test, these are alternatives to the 1 sample t-test / paired t-test. The Wilcoxon test is an alternative to the independent 2 sample t-test. And then the Kruskal Wallace test is an alternative to the one-way ANOVA. So the data types that would submit to these procedures is the same as the data types that would submit to the 1 sample test, the 2 sample test, and the one-way ANOVA. The difference here is simply whether or not we can verify that normality assumption. So the reason or the rationale for introducing this suite of tests was that we know that in many cases, it is not reasonable to assume that the variable of interest is normally distributed. So if that is the case, it means that the sampling distribution of the test statistic that we are utilizing would be incorrect, and then we could make the wrong decision about the null hypothesis. So the alternative tests are basically meant to be an alternative to those t-tests that we had discussed earlier, where if the normality assumption is not present, we can use less restrictive assumptions to still compare the centers of the distributions that we are studying. Now, each of these tests still have their own set of assumptions that are associated with them. So we still have to go through some process of checking those assumptions. But again, those assumptions tend to be less restrictive than the normality assumption because they're things like distributions are the same shape or just general symmetry, which can occur in a variety of different ways. Okay, so this is all of the material that we've actually been, that you've actually been tested on so far in the course. So that only leaves us with 2 other sections of lecture material that have not been evaluated. So those 2 sections are the simple linear regression section and the, well, I don't need the word section there, do I? And then multiple linear regression. Now, within these 2 units, we did talk about a lot of different things, right? So for example, within the SLR unit, we talked about model structure. We talked about the assumptions of said model, right? So basically what we tried to highlight was the fact that you wouldn't want to use a linear regression model if the relationship between the 2 variables was not linear. Note that simple linear regression is only utilized when you have 1 continuous or 2 continuous variables. Right, so you would have 1 response and 1 explanatory. So we talked about model structure, assumptions, the regression line. Okay, so that is yi hat equals b0 plus b1 xi. So we went over how to compute b0 and b1 for the fitted model. We talked about model diagnostics, right? So that would be like the R² value, for example. We talked about prediction from the line. So how we can find a value of yi given a value of x. We talked about inference for the fitted line. Okay, so this is going to be things like the model utility test and the prediction / conditional mean interval. There might have been a few other things in there that we discussed as well, but that's I think the majority of what we went through in that lecture set. Okay, and then in lecture set number 13, we talked about, again, model structure and assumptions. But then we didn't talk as much about fitting the line. And the rationale was because fitting the line comes from linear algebra and the background is a bit beyond the scope of the class. So we focused on starting from the point where we already have the estimates for the fitted model. So we talked a lot about interpretation of fitted line. Okay, we talked about evaluating model fit, right? So this can be done through t-tests for each parameter or the F test for model utility. Okay, right? So that means, again, that we talked about an ANOVA structure for the multiple linear regression model. That's where this F test for model utility comes from. Okay, then we talked about interaction and the effect that interaction has on the model. So we talked about model interpretation and how difficult it is with interaction. We talked about, so again, we have interpretation here. Interpretation. We talked about comparing a model with interaction to the model without interaction. Okay, so that we discussed model comparison. And we talked about how this could be done through the values like the adjusted R squared / the extra sum of squares F test. Right. Then we talked about categorical variables. And again, interpretation. Okay. And model assessments. And then we talked about the last thing was variable selection. And we talked about two things, one of which I'm going to go over in a minute, which was forward selection and backward elimination. Okay, so this would be, like a fairly, hopefully like a fairly sufficient review, like general outline, kind of big picture idea of what we've covered in the class. The only things that you haven't been tested on are the simple linear regression and the multiple linear regression material. So like you can definitely expect to see a question from each of those sections on the final, right? So okay, so expect one SLR question and one MLR question. Okay. Now from the MLR section, we did talk about a number of different things. If you consider the practice problems that I posted last night, I think there's 4 problems on that particular practice problem set, and 3 of the 4 are regression style questions. So there's 1 SLR question, I believe, and 2 MLR questions. So it's pretty clear that from the MLR material, there's a lot of things that we can discuss. The things that we haven't, so none of this has been tested via a formal test, but these 2 sections here haven't been tested on assignments or quizzes. Okay, so those are the only 2 sections that you haven't had any kind of assessment on. So it would be reasonable to expect that you should review the categorical material and the variable selection material and review the associated questions on the practice problem set while you're getting ready for the final. Because again, you can expect an SLR question, but you have seen these types of questions already, at least through assignment 6. And you can expect an MLR question, but it wouldn't be unreasonable for me to include something on, say, the categorical material, because this hasn't been tested in any capacity yet throughout the class. Now, outside of that, it's a cumulative final. Okay. So you can expect at least 1 question from each of the units throughout the course, with this being the 4th unit. Okay, so at one question from each unit. Right? So we have 3 hours to write the test, or rather you have 3 hours to write the test. So it's basically, 3 quizzes, if you will, with the same restrictions in terms of having to take the photos and upload them to CrowdMark and all that sort of thing. But again, you can expect at least 1 question from each unit on said test, which means that the test is a truly cumulative test and will be fairly balanced. 2 of those questions will be from the 4th unit, so the regression unit, and then the remaining questions will be from the other 3 units in the class. So you'll get a little bit of everything. You might not necessarily get tested on every single different thing that we studied, but you will get tested on kind of the big things that, or at least what I consider to be maybe like the main concepts from each of the units so that I can evaluate your understanding of the big parts of the course. Okay, so that brings us to 135. Does anyone have any questions for me at this point? How many questions? Will you post all these notes? Yeah, I'll post the notes. How many questions will there be? I don't know. I haven't written the test yet. The last time I gave this test, or one of the last iterations of this exam had 1, 2, 3, 4, 5, 5 questions and a bonus on it, but there was a lot of subparts. So in total, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 19 subparts across 5 questions and a bonus. That was the last time I gave it. It's not going to be exactly the same, but if that helps to give you an idea. Any other questions? Yeah, we can do that. I think you're right. I don't know if I'll get to it today, but I can do it on Monday for sure. Okay, so let me try and go over the forward selection stuff here, and then we can see how we're doing for time. So Bashir, do you have a particular question from that material? Like, is there something in particular you don't understand? I'm going to pull up the lecture notes here so that I have that as a reference, just to help direct it. Okay, what about that example? How did I assign which t-value goes into the equation? Okay, so starting on slide 46, this would be the beginning of the forward selection process. So imagine that so basically what happens in forward selection is you start from a model that has no explanatory values in it. So you have y equals beta 0. That's it. And then you go, among all of the possible explanatory values, consider each one of those separately. So in the table on slide 46 here, these t-values are for 7 different models, right? So for example, I have price, which is yi, is equal to beta 0 plus beta 1 times size. And this is the t-value associated with the coefficient for size. And then in the second slot, I have price is equal to beta 0 plus beta 1 times pool. So it's a separate model. And this is the t-value that is associated with beta 1 for the pool statistic. Okay. Does that make sense so far? So then what I have here is 7 different models, each with only one response and one explanatory value. And I have the t-value for each of those different models. Does that conceptually make sense? Okay, each of these t-values, because it's an SLR model, each of these t-values would be found using the model utility test that we conducted in lecture set 12. So if you had the raw data and you had the summary statistics for X and Y, you could calculate all of these t-values the same way that we did when we performed the model utility test of beta 1 equals 0 versus beta 1 not equal to 0 in lecture set number 12. Okay. Does that make sense? Okay. Now, basically what happens here is you pick the most significant variable. So the most significant variable is the variable that has the largest absolute t-value that would still lead to rejection of the null. So when we look at the t-values that we have in this table, 15.434 is going to lead to rejection of the null. Negative 0.538 and 0.289 will not lead to rejection of the null. Negative 23.27 will lead to rejection of the null. 12.31 will lead to rejection of the null. 0.37 will not lead to rejection of the null. And 16.5 will lead to rejection of the null. So there's 4 values that we would deem to be useful as a linear predictor for price. They are size, age, bath, and roof. Now, among those 4, we're picking the one that is most significant. And in this case, when we say most significant, we just mean has the largest absolute t-value. Yeah, you can reject based off t-values or based off the critical value. The result's going to agree, so it doesn't matter which way you do it.
Can I ask like a quick question about that? Because you just keep going through and being like, this one's a rejected one, this one's not.
Yeah.
Based on what? Like, what are you comparing it to?
Well, I'm just saying that because I know that the p-values associated with size, age, bath, and roof are going to be very close to 0. Because when you consider like the structure of a t-table and the size of the values in the table, I know where I'm going to be located. But if you want to be like really specific about it, we can do it like this. So we have 88 observations in the data set, right? So let's say that for this forward selection procedure, we go alpha is equal to 0.05. So I'm going to have a critical value on 0.02 and 86 for this particular test. So this is going to be a t-value. I need page 2, right? 88, 86. Okay, so my t-value, if I was to use the t-table, is going to be 0.025, 85, like 1.988. So I'm going to reject every time the t-value, the absolute t-value is bigger than 1.988. Or we can be like, we can do it properly too. So 8. Okay, so then imagine the t curve. Okay, so here's our t curve for this particular test. So I'm going to have a rejection region here, and I'm going to have a rejection region here. And I'm drawing them in inverse colors for some reason. Okay, does that make sense, that part of it? Okay, right, so you can see like 15.434, that's going to get into the rejection region, hence why we would reject. But anything with a 0 in the first slot, that's not going to get inside the rejection region. And then the 23.27, the 12.3, the 16.1, those are all going to get into the rejection region, but the 0.3 won't because it's just not big enough in size. So it's a fair point. Like I was kind of skipping through and saying like from looking at the values, I can kind of tell which ones are going to reject because you just don't see t-values greater than like 10. If you look at the table, you know, it's like we run from 2.578 to, so if we only had 1 degree of freedom, then we would have to check. But otherwise, if you're bigger than 10, you're going to reject for pretty much every significance level. So that was kind of why why I was skipping that part when I was explaining it. But the criteria, going back to the original question, is simply just the standard criteria that we always utilize to check for significance. So at this particular stage, we have T 0.025 and 86. Why would you go forward or backwards? Why wouldn't you just choose all the values outside the rejection region? It seems like it would save time versus going through one by one. Because every time so every time a variable enters into the model, it changes. Okay, so let me start this again. The T values are conditional values. So right now, these are all a standard T value given no other explanatory variables in the model. But once I put something into the model, the T values associated with every other explanatory variable will change. Because now the question is this variable useful given this other thing is already in the model? So if we put age in, that's going to change the T values for bath and for size and for roof. And it might even change the ones for like pool and story. So we have to check again because otherwise the wrong variable might enter the model. Does that make sense? Yeah. So this is the first step. So we set a cutoff of 1.988 and age is the most significant because it's the furthest into the rejection region, right? So that part of it's a bit subjective, but that's the idea. Does that make sense, Bashir? I don't know if she's still, okay, cool. So, okay, so now let's go forward, right? So we said age is the most important, so we've put that into the model. Now look what happens. So now we're redoing the exact same process. But the difference here is we have alpha 0.05, and now we're gonna have a T value where, oh, sorry, actually, I made a mistake. This would be on 87 because there's nothing in the model yet. No, let's just do it the proper way. So we're going to keep this at 86. It'll be less confusing that way. Okay, so now we have 0.05, but we're entering another explanatory value in the model. So this is going to be T 0.025, and now we drop to 85 because there's another variable in the model, so the degree of freedom gets smaller. So now the cutoff changes to we had to round down. So it's going to be the same thing in this case, but if we were using software, we would actually be able to get it at 86 directly. Okay, so now we have on 85, which is 1.988. And notice, compare the T values here to what was given in the previous page, right? So even if we just look at size was at 15.43 when nothing was in the model. Now that age is in the model, size is at 7.793. And pool has actually gone up to 1.361. So in this case, size is going to reject, area is going to reject, bath is going to reject. So look, area is now significant, whereas before on the first step, it wasn't. So putting age in the model completely changes the dynamic of the system, right? Stories rejects and not roof. Okay, and then we say size is most significant for the same reason we did before, and that brings us to this model. Does that make sense? All right, so I think it's going to terminate here. Yeah, okay, so now on the last step, we have alpha equals 0.05. So we have T 0.025, and now we're going to have comma 84. Okay, so this is going to give us a T value of 1.990. Okay. All right, so you can see in this case, what happens is nothing is significant. So there's no critical values that get inside the rejection region in this case. So that's when the process just terminates. So on the first step, so here, I figured out the equation in the model using the formula that are given in lecture set 12, because this is just an SLR model. But after that, everything has to be given because we don't talk about parameter estimation once we get to the multiple linear regression cases. Okay. Any other questions? So on Monday, I'll go over the question 6 from assignment number 6, the last parts that you asked about. And if anyone has any other questions, I'll be happy to go over those. And then otherwise, I'll just start doing some practice problem material. So I hope this was somewhat helpful. And as I said, some practice problems have been posted for the last 2 units. So that should give you lots of material to study to prepare for the test. And otherwise, I'll talk to you guys on Monday afternoon. And I hope you have a good weekend.